Hey students, here is our notebook for Mountains and Metamorphic Rock, Investigation 7, Week 1. It's our last real notebook before the project. And that's the last project we do. So here we go. What are we learning? We're learning about how tectonic plates at their boundaries deform and produce landforms. And we're learning about how mountains form as a result of those plate movements, those plate interactions. We're learning about how high heat and intense pressure can change a rock into a metamorphic rock. And why is it important? Plate movement and plate interactions have formed some of the most dramatic landforms and events on Earth. Mountains, earthquakes, volcanic eruptions, tsunamis. This notebook helps us to understand the causes and effects of plate interactions, and we'll understand why it matters that we live along the ring of fire and how that might impact us someday. The final project is starting next week. So what happens to the crust during plate interactions? What happens to the outer part of the Earth when the plates do their thing? When they move, when they bump, when they grind, when they uplift, when they spread apart? Okay, what happens to the crust, the outer surface of the Earth? Make your prediction. And then you're going to watch a video of the plates. These are models, right? They're models of the plates. So what happens when two continental crust plates interact? What are we going to see? So these are two continental plates. They're thick. What would you call that? What type of a landform? Maybe a mountain? Maybe a valley or a ridge? And this just kind of forms a crack. So if you go back to your notebook, we could say mountain, a valley, and a crack. And plate boundaries that are like this on Earth, where two continental plates are colliding. A really good example is where India is getting smashed into the Eurasian continent, and it's forming the biggest mountains on Earth, Mount Everest. So those are two continental plates that are getting smashed into each other. And if we throw this up and also throw up the direction of plate movement, you see that India is getting pushed into Eurasia. It's actually making the Himalayan mountains bigger and bigger and bigger every year. An O and an O plate. O stands for oceanic. So the crust that's under the ocean is dense. It's made of basalt, remember? When two oceanic plates smash together, they're both so dense, they don't really do anything. So you're going to see this person's pushing them together and nothing happens. They're both dense. They're both trying to sink. When they diverge, you have once again this gap forms, and usually a ridge with cooled lava comes up. And then here it's just kind of cracked. So for landforms that form here, not mountains, but we could say a ridge. And we would get a lot of earthquakes, right? EQs. And same for here. Anytime you have plate movement, you'd have a lot of EQs. For a plate boundary that's like this on Earth, a good example is the Mid-Atlantic Ridge. Check it out. You see the ocean is splitting apart from the ocean here. It's actually pushing South America and Africa even farther apart. Remember, they used to be connected. but they're getting pushed apart. And what's happening in this crack is new crust is forming. So new oceanic crust is forming as they're getting pushed farther and farther apart. And remember that guy Hermann Hesse, he measured the thickness of it and the age of that rock. He found that it was very young right along the ridge. It's new, then it's new crust all the time. So we could say North American and what was the other plate? Well, this is actually South American and African plate, North American and Eurasian plate. So there's 2 examples there. I don't need to write both though. Let's look at the O and the C plate model. This is an important plate interaction because you have an oceanic plate converging with a continental plate. And because the oceanic plate is denser, it's trying to sink. And look what forms. This is where a volcano is going to form. Okay, because that denser plate's going to start to melt and form magma. And when they spread apart, it really is kind of the same. It's like a gap, a valley, a crack in the crust, and earthquakes. The big deal is volcanoes form all along that boundary. Volcanoes, volcanoes, volcanoes. When an O plate collides with a C plate. So what types of plates, where is this happening? It's happening all around the Pacific plate. Because the Pacific plate is a troublemaker and it keeps ramming into all the different continental plates. Okay, the last one. This is called mid-continent mountain building. So you have one plate that's getting squished on 2 sides. And that deforms the plate. This is called folding, when the layers are folded upward. And so that forms many of the mountains on Earth is because of this mid-continent compression from 2 sides. So good example of mid-continent mountain building. Really like any fold mountains. So like on the North American plate, we have the Rocky Mountains that were formed that way. And of course, lots of earthquakes. Okay, which plate interaction that we modeled might have caused the rock layers of the Grand Canyon to lift up so high? Remember, the Grand Canyon is carved into something called the Colorado Plateau. Which one of these do you think pushed up the layers of the Colorado Plateau? Take a guess. Oh, blank page. We're going to look at some mountains and draw a picture and give some examples. Here we go. Click on the slideshow. This is all about different types of mountains. So the first and most common type is a fold mountain. We basically just saw it when we were looking at that the thing gets squeezed and it folded up. That's a fold mountain. Here's a video of it. Mid-continent uplift. Pressure on 2 sides causes it to push up and fold. Double click on the drawing. And you're going to draw this pretty basically. Zoop. 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 and show arrows. Save and close. And for some examples, let's see. Appalachian Mountains, Rocky Mountains. See the folds here and here? All right, a fault block. Breaking of the crust by compression or pulling apart happens fast enough to break rather than fold the crust. So we would picture very jagged and blocky mountains. We wouldn't see nice tilted layers. Animation. Plates slide apart, causes this whole valley floor to fall down. It's called a fault valley. This big chunky block. Double click. Scribble. And then I'm going to show that this layer used to be here and here. And then I'm going to show my arrows. Why doesn't it like my lines? I don't know. That slides that way. This slides that way. And let's see some examples. Tetons. Kind of chunky. Here's that fault valley below the Sierra Nevada. And the Basin and Range Province. Sierra Nevada. Yosemite. I'll just say Grand Tetons. Okay, a dome. I love a dome. Dome mountains form when magma pushes up under the crust without breaking through to erupt. So it's like a wannabe volcano that never erupts. Instead, the magma cools and forms hardened rock. The uplifted area is called a dome because it looks like this half sphere of a ball. So see, the magma pushed up those layers and then it just cooled. It just stopped, right? I think of it like as a zit that never pops. Okay, and it stays there forever. Yikes. So that's a dome mountain. Double click. Draw some arrows that show it pushed up. And then I'm going to add a text. Okay. I'm going to say magma pushes up rock. And then I'm going to save and close. A good example is, I'm showing you a picture of Stone Mountain. I think Stone Mountain, you can really tell from this aerial image here. See, it's like a zip that never popped. It's in the news because it has a Confederate, like a mural. Okay, so a volcanic eruption. Oh, wait a sec. I mean, we know a lot about this already, but volcanic eruptions, those are domes. They're formed when molten rock erupts and piles up upon the surface to form a volcano. They can form on land or under the ocean. This is that erupting volcano video. The stuff is just shooting out of the volcano as it erupts. And more examples: Mount Hood, Mount St. Helens. Juan de Fuca is underwater right off our coastline, and it's a volcanic mountain right by the Juan de Fuca Plate, right off our coastline. This is a beautiful volcano in Hawaii. It's a shield volcano, Monokia. I like to draw my volcanoes in a very particular sciencey way, but you can draw your volcano however you want. I like to show that a volcano is on a converging plate boundary where one plate, the oceanic plate, is subducting. Remember that fancy word, subducting, under the continental crust, which is forming a magma chamber. There's the magma chamber inside the Earth. And some smoke and ash. And we can make our beautiful lava. Oh, one more thing. This is a sea plate. Name your favorite volcano. Plateau. Relatively flat area next to a mountain that's being uplifted. They usually form near folded mountains. This is really similar to that last video. So squished, squeezed together, it uplifts this whole area and stays relatively flat on top. Himalayan mountains, Tibetan plateau right nearby. Colorado plateau was uplifted at the same time as the Rockies. So here let's show a area that will go kind of like this maybe. And show that this layer was once the same level as this layer. And we can say this kind of goes this way, and this kind of goes this way. I'm going to say Colorado Plateau. Okay. Plate movement forms all those different mountains. Cool. Well, how is that related to metamorphic rocks? And what even is a metamorphic rock? What words do you see within that word? Metamorph? Morph? Like a morphing Power Ranger? What does that mean? That's what I want you to fill in. What do you know about metamorphic rocks, and what could you say about that? That's a prediction, right? Then you can actually copy and paste the definition from the glossary. I'll do that here. And take a guess. How do you think they form? Something about heat and pressure. Well, what's going to cause lots and lots of heat and pressure on rocks? What have we been talking about? What causes lots and lots of heat and pressure on rocks? And remember, you don't want the rock to melt into lava, because then it's going to turn into an igneous rock. But heat and pressure softens the minerals of metamorphic rocks, and it allows them to rearrange. So let's take a look at some. Ooh, pretty rock number 1. Super sparkly, black, white, and gray. No reaction to acid. Let me record those observations. Sparkly, black, white, and gray. No reaction. How do I figure out what type of rock it is? Let me look in the ebook. Okay, here's the metamorphic rock section. Some of these source rocks turn into metamorphic rocks. That's the whole thing about a metamorphic rock. It starts as something else and becomes metamorphic from heat and pressure and all that plate movement, squishing and mushing it and softening its minerals. So granite becomes this rock, which is called gneiss. Gneiss has been subjected to extreme heat and pressure. So the minerals in the rock partially melt it and flatten out, and layers form. I didn't really see layers on that one. Okay, schist, highly metamorphosed, comes from different source rocks, including slate. The rock becomes flaky. Some minerals will melt and form new ones. Okay, the rock that we were looking at did look flaky. It did not look like marble, which comes from limestone. And it didn't look like quartzite, which comes from sandstone. So I'm going to go with the rock, which is called schist. And it said it was source rock could be slate, which is metamorphosized shale. So if you squish shale, and you squish it even more, it will turn into schist. How is it different? Schist is sparkly, pretty, and has more visible minerals. Shale and slate are kind of boring looking. And it's flaky. Okay, we're going to do the rest of these rocks by watching the video and using the Foss ebook. So pause my video so you can finish up those rocks. We are going to skip the metamorphic rock model because we did not have time to do it in class. But basically what we see when we do this is we use M&Ms as a model for metamorphic rocks. And it shows you how you could soften the M&Ms, not melt, soften, so that they reform in a new structure, just like a metamorphic rock. Compare granite and gneiss. What changes do you observe as gneiss forms? And if you have time, you should do that. This is the one we're really going to focus on. Sedimentary rock, metamorphic rock. This is the rock cycle, actually. It has all 3 types of rocks, and it shows you how they could transform from one type into a different type. So let's start with metamorphic rocks. How does a rock become metamorphic? We know it needs to be squished under extreme heat and pressure from plates moving and causing it to get squished. So we should say heat and pressure. For how does a rock become an igneous rock? Now we have to think back to volcanoes, right? And eruptions and molten lava and magma cooling. So what's the process? If a sedimentary rock wants to become igneous, it needs to first melt into lava or magma. So I'm going to write melting and then cooling. It needs to cool to form an igneous rock. Melting and cooling, and down here, melting and cooling. Anytime you see a red arrow, it should say melting and cooling. Okay, the final step is, how do you become sedimentary? It's not easy to become sedimentary, is it? It's a whole process. Sedimentary rocks take millions of years to form, right? It takes a whole lot of stuff to have happen. You have to be very committed if you want to become sedimentary. First of all, you need to become a sediment. How do you become a sediment? you're a big boulder, you have to be broken and crushed and thrashed and smashed, right? You have to be weathered. You have to be eroded. Then you have to end up in a basin where you're going to be piled upon by layer upon layer of other sediments until finally you can get compacted and cemented over millions of years. So it takes a lot of time, and maybe you'll have a fossil in you, and so that's extra cool. So that's a bonus. So it's a whole process to become sedimentary. First, you need weathering, erosion. You need to be deposited in a basin, compacted with all your friends. Hopefully you're friendly with them. You're going to be together for millions of years. And cementation will be the last step when you're cemented and hardened into a solid rock. Weathering, erosion, deposition, compaction, and cementation. Copy. I don't want to have to type that twice. So then anytime you see the brown arrow for a rock becoming sedimentary, it needs to go through this process. So metamorphic rock could become a sedimentary rock if it gets broken down and carried away and deposited and compacted and cemented, all that. Any rock could become any other different type of rock. On Earth, rocks are constantly recycled through these processes, right? And even a sedimentary rock could become a new sedimentary rock if it gets broken down through all those processes. Okay, so you should have all that. Save and close. And then it says down here, if you have time, you can try the Rock Column Movie Maker. It's a harder version of it. It's got all the different types of rocks. It's actually pretty fun, but we just don't have time for it. Send me on Schoology after you check out these amazing memes. Okay? Have a wonderful week. I will see you in my video next week. And that will be our final class video. Bye.